that physicists said there was a Big Bang. Okay, and they had good evidence for believing there was a Big Bang, you know, expansion of the universe and so forth, redshift and all those kinds of things. They said if there was a Big Bang, then there ought to be residual radiation left over. There ought to be some kind of background noise left from this expansion of the universe. And they could even predict the distribution of energies that would be present in this background radiation. And that's what the curve is. And so they drew out this curve, they predicted it, and then they did the science. And they aim radio telescopes at the sky and they measure the background radiation, and lo and behold, it fits the curve. Science, it works. Isn't that wonderful? So anyway, this is a beautiful example of that kind of thing in physics. And I do confess that biologists do tend to have a little bit of physics envy because they can do these kinds of things when they get these simple numbers out. You know, they're looking at such simple stuff. It's easy for them to do. We biologists look at much more complex examples. And I'm going to talk a little bit about the Cambrian explosion. So the Cambrian explosion is a kind of Big Bang in the creation of life. And then what happened is about 500 million years ago, we made a sudden transition. Sudden meaning roughly 10, 20 million years. So not instantaneous, but you know, 10, 20 million years on a geological timescale is a pretty short period of time. There was a fairly sudden transition where we went from a world that was largely full of single-celled organisms, bacteria and protists and plants and algae and those kinds of things, to one where we had a large number of things like us, multicellular creatures, where what happened is that it seems a lot of cells got together to produce more complex structures that could do more complex things. What was happening there? Well, it's like the Big Bang of physics. One way you can look at what happened 500 million years ago is you can look at the background radiation. That if all these protists and bacteria and plants were making transitions, what you ought to be able to do is look at modern protists in particular and ask, do they show any of the diversification of molecular processes that we express in our bodies? Are there hints in protists of the features that we find in things like us? This is citing a good paper there that just came out from Farmer and Habura. If you haven't read it, I recommend it. It's a really good paper that talks specifically about cell biology and we're seeing more and more of these papers come out, and is directly refuting many of the claims of the intelligent design creationists. Okay, so one example. This is one of my favorite critters. It's a beautiful little animal. It's called a quantiflagellate, and it's a protist. It's a eukaryote. It's a single-celled eukaryote, and it's got a fairly simple lifestyle. It's got a whip-like flagellum, so it's got the little thing that spins out there like a little propeller, and that little propeller generates vortices of current that draw in particles in the water towards the cell body. And then what happens is they get trapped on this little collar, this fringe of cells, or a fringe of processes on the surface of the cell. It's very simple. But it's been suggested that this might be a precursor to multicellular life. Why? Well, because if you look in a sponge, for instance, you find the same kinds of cells permanently locked together in a matrix. When you look inside of a sponge, you find all these cells called choanocytes that look just like that, except that they're not free-swimming, single-celled organisms. And they're doing the same thing. They get a little whip that spins around, and it draws water through the tubes of the interior of the sponge, and then it has this collar of processes that act as filters to trap anything that's coming through the water, and then they ingest it. Also, when you look at these protists, they've got some interesting behaviors. They're not always acting alone. Sometimes they'll do things like is illustrated on the left there, where they will cluster together, and then they work as a unit, having all their flagellae out there, generating vortices that more efficiently bring more particles in towards the group. You also see coordinated behavior in motion, that these are animals in the water column, and many creatures in the water column will do this vertical migration over the course of a day, when the sun comes up and the sun goes down, and they will sometimes team up at dusk and dawn and aim all their flagellae in the same direction and more efficiently move in the direction that they want to go. So they've got these examples of coordinated behavior. Now, the other thing they've got, and this was a little bit of a surprise, is people looked inside their genome, and in particular, this is the work of Nicole King. They looked inside their genome and they discovered that they had certain molecules that are in common with us. So again, radiation of that Big Bang in the Cambrian explosion, that we would predict that some of the features of us would be found in these protists, and there they are. In particular, there was a molecule called a receptor tyrosine kinase. Our receptor tyrosine kinase is it's a protein that sits on the surface of many of your cells, and it's got a sticky part on the outside that can bind to other cells or other targets, and it's hooked up to an enzyme called the tyrosine kinase, which acts as a molecular switch. It activates a whole bunch of other processes inside the cells. And ultimately what it can do is it can turn genes off and on. So this is a really useful molecule to have. It's a cell now, it has something on its surface, it bumps into something appropriate that matches that particular protein, it will activate a set of genes inside the cell and change the behavior of the cell. It's exactly what all of your cells do during development. So, you initially start out as one cell, that one cell divides many times, you get this mess of nearly identical cells, and they have to start interacting with each other and decide, oh, well, you're going to be the pancreas and I'm going to be the liver. And the way they do this is they have proteins that interact with each other and inform the other cell and yourself what you're stuck to. So receptor tyrosine kinases are an example of this. And for a long time they were thought to be unique to multicellular animals, to metazoans like us. And they were found by surprise in quinoflagellates. They are not present in plants and fungi. However, we can also see where it came from. In plants and fungi, you do have these things called EGF, epidermal growth factor. It's a receptor protein without the enzyme. And you also find the enzyme, the tyrosine kinase, as separate genes. And what's happened here is that there's been a fusion of these two to make a pair, or to make a complex that can function in new and novel ways. Similarly, when you dig deeper into the quinoflagellate genome, you find lots of things. As I mentioned, there's these receptor tyrosine kinases that act as switches. They also have cadherins that were once thought to be unique to animals, multicellular animals, which acts as a kind of glue between cells, a very useful kind of glue that can respond to concentrations of calcium and either be watery and liquid and let things go through it, or it can firm up and lock things in place. And integrins, these are proteins that bind to extracellular proteins, which we use to connect our cells, for instance, to a framework, an extracellular matrix that we find all over underneath our epithelial cells, and which quinoflagellates seem to use as part of their glue trap to capture bacteria and particles from the water. So here we've taken something that's used as a glue trap and we've used it to make glue to hold cells together in multicellular animals. Again, it's using an existing function in novel ways to generate more complexity. Another example, this is Trichoplax. Trichoplax is a pretty cool creature. It's a little flat disc that apparently only has 4 different cell types. It's about the simplest multicellular animal that exists. It is the simplest that I know of. All it's got is on its surface, it's got a sheet of cells that acts as an epidermis, protective layer. It's got an internal layer with cells that seem to be kind of stretchy or elastic that may be acting as kind of muscles to help it crawl. And then a bottom layer that contains a couple of cells, some of which secrete enzymes, particularly digestive enzymes, and some of which are absorptive. They just soak up whatever gets broken down by the digestive enzymes to eat. So it's like a little patch of stomach that's crawling over the surface of rocks and digesting whatever it contacts and soaking it up. It's a very simple, elegant lifestyle. Well, these creatures are pretty cool, very simple. They look in their genome and what do they find? They find complexity. Complexity that you would think they didn't need. What they have is they have a bunch of very cryptic proteins up there. You don't need to know those names. But if you're a developmental biologist, you're very familiar with these names. These are molecules that are used in all kinds of signaling events in embryonic development that we use all the time to identify tissues and organs in our growth. And there they are, sophisticated cell signaling molecules inside an organism with only 4 cell types. Surprisingly, they also have a full suite of ion channels.